Good afternoon. During the last lecture, we considered the example of a graph of a function f having a critical point q, and we computed the matrix which represents the Weingarten map WP at the point P given by the image of Q by the surface patch sigma. We found that this matrix is a matrix whose entries are the second derivatives of f at the point x0, y0. Now I want to show you 4 examples of graph of a function f having a critical point at x0, y0 equal to 0, 0. So examples of graph of functions having a critical point at x0, y0 equal 0, 0. The first example is the one of the function f of x, y equal 1 minus x squared plus, minus 2y squared. So how the graph of this function looks like? It looks like this. This is a point P equal f of 0, 0. This is the normal vector at this point, and for example, the red line is the curve gamma equal to sigma of x0 plus t y0. This curve has the property, gamma t, that gamma 0 is sigma x0 y0 equal p, and gamma prime 0, this is E1. Instead, in red color, I will mark the curve gamma tilde equal sigma x0 y0 plus t. This curve has the following properties. Gamma 0 is sigma of x0 y0 equal p, and gamma prime 0 is equal to E2. So I should write also that this is E1 and this is E2. Now, what is the matrix WP for this graph. It is given by WP equal negative 2, 0, 0, minus 4. And as you see, is a diagonal matrix with negative entries on the diagonal. Let's try to associate the sign of the entries of the diagonal to the behavior of the normal vector along these two curves. So if we sketch this curve on the blackboard, it has a behavior like this, and along this curve the normal vector varies like this, and when you have this kind of configuration, the entry of the metric is negative. Let's also write E2, E1, sorry. And what about the red curve? It's a curve like this, where this is a point P. E2 is this vector here. It points orthogonally to the blackboard, and this is N. This time the behavior of the normal vector to the surface along this curve is this. And in both of cases you realize that N behaves to the plane spanned by N at P, and the vector which is the initial velocity of the curve we are considering. So in this case N varies this way, in this case N varies this way, and in both of cases the entry of the corresponding entry of the matrix which you represent by Cartan map is negative. Now let's consider another example where f is given by x squared minus y squared. In this case, the graph of the function looks like this. And suppose that the point P is this one. P is f sigma at 0, 0. This time, what happens if we look at the curve gamma t having initial point equal to P and initial velocity E1, and the curve gamma tilde having initial point P and initial velocity E2. So first of all, let me complete this picture. So the yellow curve would look like this, instead the red one like this. This is E1 and this is E2. Now let's try to sketch the curve separately. This time the curve in yellow looks like this. This is point P. This is E1. And the normal vector to the surface varies this way. The corresponding entries, the corresponding entry of the matrix which represents WP is positive. And instead, if you look at the red curve, it looks like this. So E2 points orthogonally to the blackboard, and N tilts on remaining on the plane spanned by N and E2. In this case, the corresponding entry of the matrix is negative. The next example, let's erase this part. Is the one where f of x, y is 1 minus x squared. The graph of this function looks like this. Suppose that this is p equals sigma 0, 0. Then in this case, the yellow curve looks like this, and this is E1. Instead, the red curve is this, and the E2 points like this. In this case, the matrix which represents WP is given by -2, 0, 0, 0. And the reason is that the yellow curve passing by P with initial velocity given by E1 is this one, and the N along this curve varies this way. N also in this case belongs to the plane spanned by N at P and E1. The corresponding entry of WP is negative, and the reason why there is a 0 is that, this 0 here, is that N belongs to the plane spanned by E1 and P, and it has no component along E2 which is orthogonal to the blackboard. Instead, the reason why there are two zeros here is that the curve gamma tilde, I forgot a tilde here, excuse me, is just a straight line. And this is E2. So as you can see, the normal vector to the surface along this straight line does not tilt at all. It points always in the same direction. This is why the components of WP corresponding to this direction are 0, 0. And another example which is a bit more complicated is the one of the function f of xy equal 2xy whose graph is this. Approximately. This is more difficult to sketch. This is P is equal to sigma 0, 0. This time the yellow curve it's like this. This is E1, this is N, and the red curve is like this, E2. The corresponding matrix for WP is 0, 2, 2, 0. This time we don't get a diagonal matrix, and the reason is the following. Let's sketch the yellow curve and the behavior of n along this curve. So this is P. This is n at P. This is E1. What about n along this curve? We have that n rotates. So we have n rotates this way. Instead, if we move along this half line, n rotates this way. So n tries to become parallel to E2, which is orthogonal to the blackboard. This is why there is a 0 here. So WP of E1 has no component along E1. It has a non-zero component along E2, and it is positive. Similar behavior. Similar is the behavior of the vector field n along E2, the curve parallel to E2 at P. So this is P, this is E2. This is n at P. Also along this curve, the vector n rotates. It rotates this way if we move in this direction, and it rotates this way if we move in this direction. So essentially it tries to become parallel to E1. This explains why WP of E2 has a component along E1 and a zero component along E2. In this example, in all of these examples, the matrix associated with WP is always symmetric. This is not a coincidence. It is possible to prove this lemma if S is an oriented surface and P is a point of S, then WP is represented by a symmetric matrix with respect to any orthonormal basis of TPS. The book provides you with two proofs. I will present only one of these two proofs. There is one proof based on the use of the inverse function theorem, and another proof which is based on the linear algebra material, precisely self-adjoint linear transformation. So, in order to present the second proof, which is, in my opinion, the most interesting, we need to review some material you studied during the linear algebra course. Let's start by the following proposition. Definition. .6. So let nu contain in R3 be a two-dimensional subspace a linear transformation W defined on nu with values in nu is said to be self-adjoint if it satisfies the following equivalent conditions. One, there exists an orthonormal basis for nu with respect to which W is represented by a symmetric matrix to with respect to any orthonormal basis for nu W is represented by a symmetric matrix, and condition number 3, these two inner products coincide. Let's prove that the conditions 1, 2, 3 are equivalent. So proof of the equivalence. We will prove that three implies two implies one, and one implies three. Clearly, the fact that 2 implies 1 is obvious. Why? Because if W is represented by symmetric matrix with respect to any orthonormal basis of nu, implies that it is true that there exists an orthonormal basis for nu with respect to which W is represented by a symmetric matrix. Let's prove that 3 implies 2. So unfortunately I have to erase something. So remember that condition number 3 is that these two inner products coincide. Let's prove that with respect to any orthonormal basis for nu, W is represented by a symmetric matrix. In order to prove this, let's suppose that the matrix which represents W is given by A, whose entries are A11, A12, A21, A22. With respect to the basis V1, V2. Okay, it is clear that W of V1 is A11 V1 plus A21 V2. Precisely A11, A21 are the elements of the first column, and W V2 is A12 V1 plus A22 V2. Now we want to use this fact to prove that this is a symmetric matrix. In order to do that, we have to observe that if you consider W V1 multiplied by V1, you will get A11. If you consider W V1 multiplied V2, you will get A21. If you consider W V2 V1 you get A12, and if you consider W V2 V2, you will get A22. If you want a formula for A11, A12, A21, A22, you can then write this one, Vi multiplied by Wvj, this is Aij. Now, if you want to prove that this matrix here is symmetric, you have to prove only that A12 is equal to A21. But this is equivalent to prove that V1 W V2 coincide with V2 W V1. But this follows from this formula. Now it remains to prove it remains to prove 1 implies 3. So 1 says that the matrix which represents W is symmetric if we use a specific orthonormal basis, and 3 is this identity. So we have to prove that this is true. So let's write down X as A, v1 plus bv2 and y equal to cv1 plus dv2. Then wx multiplied by y will be wav1 plus bv2 cv1 plus dv2. And now you use the properties of the inner product, and in particular the bilinearity and the linearity of W. And you can write this as AC WV1 V1 plus BC WV2 V1 plus AD WV1 V2 plus BD WV2 V2. Now we use the fact that the matrix is symmetric. This means that WV2 V1 and W V1 V2 coincide with V2 W V1 and V1 W V2. Why this is true? This is true because this is A12 and this is A21. This is A21 and this is A12. So this term and this term can be replaced by V2 WV1 and V1 WV2. So this means that this can be written as AC V1 WV1 plus BC V2 WV1 plus AD V1 WV2 plus BD V2 WV2. And this is nothing but then AV1 plus BV2 W of CV1 plus DV2, which is exactly the product of X and WY. So we prove that WXY is equal to the product of X and WY. The next result that we want to prove is about the matrix which represents a self-adjoint linear transformation. It says that if we choose carefully the orthonormal basis, then the matrix is not only symmetric, but it is diagonal. So if W from nu into nu is a self-adjoint linear transformation, then there exists an orthonormal basis V1, V2 of nu with respect to which W is represented by lambda 1, 0, 0, lambda 2. So in other terms, V1, V2 are the eigenvectors of W, and lambda 1, lambda 2 are the eigenvalues. Let's consider an auxiliary function Q defined on nu with values in R, defined this way: QV equal to the inner product of V with WV. Let S1 denote the subspace of nu which is a sequel of vectors in nu having a length equal to 1. Since S1 is compact, then Q achieves a minimum value that I will call lambda 1 at some point V1 in S1. Here I am using a lemma that you can find in the appendix. Then let V2 be orthogonal to V1 and set lambda 2 equal QV2. Then if we reuse this information, then we have that the matrix which represents W has this form: lambda 1, lambda 2, B, B. Why? Because we saw before that Aij is Vi Wvj. So lambda 1 is V1 Wv1 equal QV1, and lambda 2 is V2 Wv2 equal QV2. We know that the matrix is symmetric by previous result. Now it remains to show that B is 0. So what is B? B is V1 Wv2, but also V2 Wv1. Okay, an arbitrary vector V in S1 can be written as cosinus of theta V1 plus sinus of theta V2. Remember that V1 and V2 are our orthonormal bases. So any other vector in S1 can be written this way. We need to compute Q at V. If you make this computation, you will find lambda 1 cosinus square of theta plus 2b cosinus theta sinus of theta plus lambda 2 sinus square of theta. If you study this function, you will find that Q of V seen as a function of theta has a global minimum at theta equals 0. But V of theta equals 0 is V1. Then what happens if we compute d theta of QV at theta equals 0? You get that this is 2B. And this one must be 0. And this says that B must be 0. Okay, now we introduce some new tools whose definition is inspired by this proof. So we have a proposition, definition, 4.8. The quadratic form associated to a self-adjoint linear transformation W is Q defined from nu with values in R, defined by Q of V equal VWV. If V1, V2 is an orthonormal basis, with corresponding eigenvalues lambda 1 smaller or equal to lambda 2, then Q of cosinus of theta V1 plus sinus theta V2, this is lambda 1 cosinus square of theta plus lambda 2 sinus square of theta. And in particular, you have that lambda 1 and lambda 2 are respectively the minimum and the maximum values of Q on S1, where S1 denotes once again the set of vectors of length equal to 1. One remark I want to make is the following. The knowledge of Q completely determines W. In order to show this, we use this trick. You evaluate Q at x minus y. By definition, this is the product of x minus y with W x minus y. And using the bilinearity of the inner product and the linearity of W, you can write this as x wx plus y wy minus 2 times x wy. But this is q of x, this is q of y, consequently you have that x wy is given by 1/2 q of x plus q of y minus q x minus y. And once you have this formula, you can compute wy for any y. Now we are ready to give the proof of lemma 4.5. I will write it again on the blackboard. If S is an oriented surface, sorry, I omitted one word, regular surface, and P is a point of S, then the Weingarten map WP is represented by a symmetric matrix with respect to any orthonormal basis of TPS. Okay, so what we want to prove is this identity WP of sigma u q is equal to WP sigma v q sigma u q, where sigma from u into R2 in S is a surface patch, Q is a point of view, and why this is enough? It's enough because this implies that WPXY coincide with XWPY for any pairs of vectors x and y chosen from the basis sigma u q sigma v q of TPS, where P is as usual sigma q. And this implies that the matrix which represents WP is symmetric. Okay, so how to prove this one? We start observing what follows. Let's consider the map N composed with sigma at Q. This is a map defined on U, which gives you a vector which is orthogonal to sigma UQ. Why? Because this is a vector which spans TPS, and this is a vector which is orthogonal to the surface. Then this means that the map Q goes to the inner product of N composed with sigma evaluated at Q multiplied by sigma U Q. This is identically 0 on U. if this is the function identically 0, its derivative will be 0. So we consider the partial derivative with respect to v. And here I am dropping the symbol for q to make the computation easier. So this is equal to n composed with sigma u, v, sigma u plus n composed with sigma uv. So this implies that this is 0, of course, or maybe let's write here equal to 0. This implies that this term is equal to negative n composed with sigma uv. If you exchange the role of v and u, you can prove also that n composed with sigma u multiplied by sigma v, this is minus n composed with sigma vu. Since sigma is a smooth map, then these two functions coincide. And this says that this function is equal to this function. Okay, now let's try to write down this identity in terms of the Weingarten map. You know that WP of V is minus dn at V. Let's ask ourselves, what is this? N composed with sigma u is nothing but then minus WP sigma u at q, because if you want to compute this derivative, you have to use the chain rule. So by chain rule, this is the n evaluated at sigma u. But the n evaluated at sigma u up to a sign is the Weingarten map at sigma u. In the same way, this one is minus WP sigma V at Q. The reason why there is a Q here is that there is a Q here which I omitted. Okay, so what does it say, this identity? it says that minus WP sigma U at Q multiplied by sigma V at Q is equal to minus WP sigma UQ, sigma VQ multiplied by sigma U at Q. And you can multiply both sides by -1. And this is the identity I wrote on the blackboard before and that I wanted to prove. So the matrix which represents WP is symmetric, and for this reason WP is self-adjoint. Okay, now I want to introduce a bit of notation. Instead of writing n composed sigma U and n composed with sigma V, I will write NU and NV. The computation we made before, this one, maybe I should write. Okay, it's enough. So this will be written as Nu sigma V equal NV sigma U. We saw before that N composed with sigma V sigma U is equal to minus N composed with sigma UV. This will be written as N V sigma U equal to minus N sigma UV. And the identity N composed with sigma U multiplied by sigma V equal to minus N composed with sigma UV. This will be written as N V sigma U equal minus N sigma UV. If I want to be precise, this should be sigma VU, but they are equal, so I can write sigma UV. And a similar computation allows you to prove that n u sigma u is a minus n sigma u and n v sigma v, this is minus n sigma vv. And instead of writing w sigma q of sigma uq, for example, I will write just w of sigma u, and instead of sigma w sigma q of sigma v q, I will write w of sigma v. Okay, let me check how much time I have. 30 minutes. Okay, let's introduce now the notion of normal curvature. Definition 4.9. So let S be an oriented regular surface and let P be a point of S. Let V1, V2 be an orthonormal basis of TPS. And suppose that the matrix which represents the Weingarten map is K1, 0, 0, K2. This basis exists by proposition 4.7. Then we have the following. One, the eigenvectors plus or minus v1 plus or minus v2 are the principal directions of S at P to the eigenvalues K1, K2 are the principal curvatures of S at P if K1 is equal to K2, then P is an umbilical point three. The quadratic form associated to the Weingarten map is the second fundamental form of S at P. This is denoted by this symbol 2P of V. Actually, I should write this way, sorry. And this is a formula where V is a vector in TPS, of course. Finally, the definition of normal curvature for if V is a tangent vector with length 1, then second PV is the normal curvature of S at P in the direction of V. Let's make a few remarks. So if K1 different from K2, then V1, V2 are uniquely determined up to the sign Instead, if K1 equal to K2, that is P is an umbilical point, any vector of length 1 is a principal direction. This implies that you have plenty of orthonormal bases for TPS. I want to show two examples of surfaces with umbilical points. The first one is the plane. For the plane, WP was the linear transformation whose matrix was this. So in this case we have K1 equal to K2 equal to 0. So any point is an umbilical point, and any vector of length 1 is a principal direction. The second example was a sphere. We saw that WP was minus 1 over R minus 1 over R 0, 0. Of course, we are considering a sphere of radius R. So also in this case, any point is an umbilical point, and any vector of length 1 is a principal direction. Instead, the graph I presented before, okay, let me find again. These graphs share a common property. So we saw that for the first one, the matrix which represents WP was minus 2, 0, 0, minus 4. For the second one, we had 2, 0, 0, minus 2, 3, and in this case, the basis was U1, E2. So in this case, in these three cases, plus or minus E1, plus or minus E2 are the principal directions. Let me check how much time I have. Okay, I think it's a good point where to stop. Thank you for your attention.